So this is where I have to remember what I was going to talk to you about before lunch. So thank you very much for listening. Now, Monica has just given a wonderful presentation. She's told you exactly why equivalent circuit network models are not the best thing to use. I'm about to give you a presentation showing you all the wonderful things you can do with equivalent circuit network models. Bear with us. We will be moving on to use Monica's models in due course, but I'd like to show you what we've been able to achieve already. So I'd like to start by introducing the Rebbe project. We've heard about that from Monica before. I'm going to say a few more things about it. And I think if Nikita's around from Ricardo, she's going to say even more about it tomorrow. I'd like to introduce Cranfield's team and our facilities and talk about how we've been doing state-of-charge estimation for lithium-sulfur. We've developed two sets of practical methods that really work. One of them is based on Kalman filter derivatives. The other one is based on ANFIS, adaptive neuro-fuzzy inference systems, a technique from computer science. I'd like to talk about the progress we've made and the future directions we're taking, and then end with the usual acknowledgements and conclusions. If you would like a simple model of a lithium-sulfur cell for free, you can download ours from the MATLAB file exchange. That's just a plug for that. So the Rebbe project, revolutionary electric vehicle battery. Many people ask us what was Rev A, but I suppose that was probably lithium-ion. Rebbe, revolutionary electric vehicle battery. This is a big project. It's led by Oxis Energy, and the other partners are Imperial, Ricardo, and ourselves. And the aim has been to develop a prototype electric vehicle battery pack with cells achieving 400 watt-hours per kilogram, operating at over a temperature of -10 to +55 degrees Celsius, and with a life of 615 cycles. Now, I'm not here to tell you about those aspects of that. Other people will be able to fill you in on how much we've achieved. My work package has been looking at the battery management system algorithms, and that's what I'm going to talk about today. So for lithium-sulfur, there's a couple of challenges for state estimation. Coulomb counting doesn't work. People have alluded to things like the shuttle effect and the fact that there are multiple chemical pathways through the sulfur cell depending on how you use it. There's also a high rate of self-discharge. But the bottom line is that one of the industry standard techniques for battery management systems is to just integrate all the current that you add in or get out of your cell, and that gives you a reasonable estimate of the state of charge. It can work very well for lithium-ion in some applications. It doesn't work well for lithium-sulfur, so we can't really pursue that. The other problem Monica alluded to earlier is the unhelpful shape of the OCV curve. You can see here this shape. We saw this in David's presentation at the beginning. If you're reading off a voltage, you're fine if you're in the high plateau, but if you're in the low plateau, that's almost flat. Any point there's two different places you could be. So the naive, sort of straightforward techniques that do work very well for some chemistries can't be applied for lithium-sulfur, sorry. Computational complexity is also an issue. People make very good models of batteries, but if they can't run on an ECU, then they're not a lot of use for an in-situ application. So the mandatory mugshots of our team. Thank you very much to all my colleagues who helped with this work. We have my colleague Stefano, Abbas, Karsten, not strictly a colleague, but very helpful anyway. We have Václav from Aalborg, and this is the team that's done this part of the work. And I will mention at this point, thank you to Raj and her colleagues at Oxis, Monica and Greg and Teng at Imperial, Leon, Nikita, and all the others at Ricardo. Thank you for your contributions too. Here are our facilities, part of our mechatronics lab. Now this just looks like a slide full of equipment, but let me talk you through it a bit there. What we have is an oven with a two-way current source, and we have a pack of lithium-sulfur cells inside that. So that gives us our temperature-controlled environment. We're able to apply duty cycles as we choose and adjust the temperature to replicate a real automotive environment. That's connected up to a hardware-in-the-loop vehicle model rig. Parts of it are software-based, parts of it are hardware-based. We've got real motors and real power electronics to give us the right sort of transients and give a reasonable, realistic feel of what we're going to see on the real car. We can operate with cells or small packs. We can simulate automotive duty cycles and others. And there's a couple of posters to see by Abbas and Carsten, so do look out for them in the application section. We've used two families of techniques for state estimation. The first one comes from control theory. Now, a control engineer is somebody who gets given stuff and told, we've built this, make it work, please. That's what we do. And the basic assumption we make is that the model of the system you've given us is not completely wrong, but it's not going to be perfect either. Uncertainty is a huge thing for us. So we know the equivalent circuit network model is not going to be right. Lithium-sulfur isn't an equivalent circuit network. That doesn't mean we can't do something useful with it. That's the key thing. The model we know is wrong, but we can still use it despite that. We use some formal techniques. Professor Rudolf Kalman developed something called the Kalman filter, and that's an example of a technique that blends modelled insights. So if you have a model, you can sort of use that together with the observations, and by combining the two, the model tells you where you're going, the Kalman filter tells you when you've gone off course and steers you back. So if your state of charge is going down faster than the model is predicting or going down slower, you get an error signal. Your measurements are different from what your model says, so the Kalman filter algorithm automatically adjusts the model. There are limits to how well it can perform, and there are several flavors of Kalman filter, but that's one of the things we've been using, and it's worked very well for us. Usually in practice, people tune parameters by trial and error. We've tried to be as physically representative as possible. The basis of what we've been doing so far has been equivalent circuit network models. We've fitted them using our own techniques. We found that worked better than lots of the things you see off the shelf. And the basic idea is to apply something called the prediction error minimization technique. It's a well-known thing from system identification and control theory. You can see an excellent description of it in Leonard Young's textbook, System Identification, the textbook on system identification. We can fit equivalent circuit network models very quickly indeed, so much faster than real time. And that's very useful. We can parameterize a huge amount of data in a matter of minutes. So before we did this, we had a very manual process that our collaborators were having to go through. It took quite a lot of effort and a lot of human intervention to fit these models. We can now do it better and faster. So minutes for a day-to-day. We do this for a pulse discharge operating at different pulses over an operating envelope, so we cover the whole state of charge envelope, and we do this for multiple temperatures. And we do this with the pulse discharge, but we then validate it with automotive duty cycles. So this graph here, we've used the new European driving cycle, which is neither new and not really a driving cycle, though it is European. We've also used things like the Artemis test cycles and the World Light Test Procedure, which are much more representative of what you really do see on the road. But the important thing is that if you identify your model for round about the same sort of power load as what you're going to see, this does seem to work quite well. So if you do double the power, you do start to see some deviation. If you quadruple it, you see more. But if you're reasonably representative of your duty cycle with your test data, then we found that for these driving cycles, it works well. One thing to bear in mind is that from a system identification point of view, horrible cycles are great. There's a lot of information content when there's a lot of stuff moving around. So for us, a duty cycle, like a driving cycle, is far easier to deal with than a constant charge or discharge. That's actually quite hard. There's not a lot of information there. The fit wasn't perfect, but it was better than anything anyone had seen before, so we were all very pleased with it. And you can read more about that in the journal paper. Now, these things have been used for Kalman filter family estimators. We've looked at several different algorithms. The Unscented Kalman filter is the one we've settled on as our favourite. But you can see here in these graphs, we can track the state of charge quite well. The top graph shows the effects of shows the extended Kalman filter, which is the simplest algorithm. Now, what you can see there is that it works very well indeed, providing the state of charge initial estimate is reasonably good. If you want to get better performance when you don't know the state of charge, the unscented Kalman filter is a lot better. So what you're seeing on the graph below isn't poor tracking at high states of charge, it's just the time taken to converge. Once you've converged, the next time you charge up, it will stay converged. So there might be an issue with self-discharge in an application, but fundamentally the unscented Kalman filter is very good at coping with unknown states of charge. We were very pleased to discover that Ficosa, who Geordie from Ficosa is here, has a poster showing that they've independently managed to take our estimators and put them in their own battery pack and got good results with this one. So that's great news. It does work. We've also applied a different set of techniques, which is techniques from computer science. Now, we've started by looking at the relationship between the parameters and what information you can get from them. As we know, and we've established this formally, this open circuit voltage curve is not so good, and there's a mathematical justification for why that's the case. But what you can do is you can get a lot of information from combining the OCV curve and the resistance curve. So if you can get a real-time estimate of those parameters, there's enough information in both of them to tell you roughly where you are in terms of state of charge. So again, we've implemented this, tested this out on real cells with realistic duty cycles, driving cycles, and we've been able to get a mean error of 4% using those techniques, a peak technique of a peak error of about 7%. And I know Leon and Nikita's team have been working at implementing these in a pack, though I think we're a little bit off, having actually got everything working there. But we have proved this in our own test hardware, and we know this does work as well. So where were we last year? Before the Rebbe project, there were no embeddable models of any kind, at least none that we were aware of. There were no estimators. Last year, we demonstrated the equivalent circuit network models. The publications were still in the peer review process. We'd started on the Kalman filters, we got some early results, and we were preparing a paper. And we'd got early ANFIS estimators ready, and again, still in peer review. We've moved things on from that. You can get our example of an ECN model from the MATLAB file exchange. So if your engineers want to, your application engineers want to use something that isn't lithium-sulfur but's close enough to give them a feel for how it behaves, that's there. You may need to reparameterize it for different cells. In fact, you will need to parameterize it for different cells, but it's a good starting point. Our Kalman filter techniques have been implemented and published and successfully replicated by Geordie's team. We've got a more advanced version of that. I haven't spoken about that today, but that's in peer review, and that performs even better and gets rid of some of the remaining issues that we saw with robustness, so an even more robust algorithm. The ANFIS estimators have been developed. We're actually fusing some Coulomb counting into that system as well. The Kalman filters do that automatically, and that's in peer review. So some future directions. This ties in quite nicely with Monica's slide and shows where these packages of work fit together. If you like, there's a modelling stream, and that's on the left, and an estimation stream on the right. The colour coding, red, amber, green, gives you an idea of their state of maturity at the moment. You can see that estimators lag models by a little bit of time, as you'd expect. You can't build an estimator using a model that doesn't exist. Now, I'd like to emphasise that the box on the left, that's work by our collaborators, in particular Monica, Teng, Greg and their team. The ECN models were a group effort. Now, at the moment, we've got ECN-based estimators. You've seen the early zero-dimensional electrochemical models from Monica's team. We've heard about how there are still some things to go there, like the temperature dependence, but there's enough there for us to get started and to see what we can do in the estimator space. So that's something we're actively working on at the moment. So in parallel with Monica's team developing their mature models, we are developing estimators to see whether we can take those into account to prove that we can. We've made some good progress there. Having done that, Monica's touched on spatially distributed electrochemical models. We've seen already about the 1D model. There are some excellent techniques from the University of Oxford, from David Howie's team there, that apply Chebyshev polynomials to do efficient spatially distributed modelling work. And we'd like to apply something similar there. It's going to lag because we need the models before we can do that. Another area of work, we're looking at degradation modelling through ECN parameter changes, so changes in resistance and capacity terms. Václav, who's over there, is working very hard on those and has got some good results. The paper is in preparation and we'll be submitting that very shortly. We're also looking at an air application, the Airbus Zephyr program. Now, I think Sarah's going to tell us more about that tomorrow, so I won't say very much there. We have got the best postdoc job in the world advertised at the moment. So if you or anyone you know would love to work in Cranfield, now Cranfield's great, it's a beautiful English village, and you get to work with our wonderful team over there. Am I plugging this enough? But anyway, we'd really encourage applications for that, and we're also continuing to look at automotive applications too. So our acknowledgements, this work was funded by the EPSRC and Innovate UK. I'd like to thank the co-authors of this presentation and our many other colleagues and collaborators, particularly Oxys, Imperial, Ricardo, and Václav. So thank you very much. Okay.
Thank you, Daniel, for that really nice talk. Floor is open to questions. Let me start then. I'm sure you get asked this really often. State of charge, what of state of health?
Well, what do you mean when you say state of health?
I guess you ended up touching on it because with Václav's models, you've started on that track, as it were. So do you think we are going to need to make mechanistic models for state of health estimation before you're able to estimate it, or do you think you'll be able to possibly work in tandem for that?
That's something we're exploring at the moment. Now, to my mind, working in the applications, state of health can mean two things. It means your ability to deliver power, and you can get power fade, or it can mean your ability to deliver capacity and range, so you get capacity fade. Which is more important for you is going to depend on your application. And I'm sure they often do go in parallel. I'm not sure the extent to which we could predict in advance how those would go. I think data-driven work is the best way we have of doing that. But what we believe we can do is we do believe we can work out how much your resistance has increased, how much your capacity has faded. And that's work that we're preparing at the moment, so we'll see what we can do with that. We can always do more with a better model. So when there are better models that have scientific basis and make real sense, these are better than something the control engineers just make up. I mean, we make up something sensible, but if there's the science there, we can do better. We can use that to push ourselves further.
These control algorithms, you use the same type of methodology, or you need to go for a different one?
We are looking at the similar methodologies there. So the question was, for the physics-based models, are we going to use the same methods or similar methods to those that we've used for the equivalent circuit network models? And the answer is yes. It is a set of differential equations. So the techniques such as the extended Kalman filter and so on are are equally applicable to that situation. I think it's more difficult to see how we'll use the ANFIS techniques, but I only say that because we haven't spent time thinking about it, not because I think there's going to be a problem there. So watch this space. We'll let you know how we get on.
I think we have time for one last question. Okay, we have Laura, and then we have Professor Omar.
For an application that has a constant current charge and discharge, can you use what you've developed already and just modify it, or will you be starting from the bottom again?
A constant discharge and charge is a challenging scenario for a system identification experiment. And the bottom line is that you don't have a lot of information when you've got that sort of thing. You get a lot of information about the resistance through the dynamic behavior of your system. What we are expecting to do is we're talking with our collaborators at your company, of course, who you know, Bob, about ways of changing the duty cycle. And to give an example of that, if you've got a battery pack and you're using 75% of the capacity of that, if you've got 4 parallel strings in it and you can switch between the 4 parallel strings, that still gives you your same power capability, but the switching transients give us enough information to get something out. Other techniques that could be used would be adding some artificial pulses there. I can think of parallels in the aircraft industry where you occasionally want to diagnose the state of your ailerons and things like that. So you just stick a little bit of a pulse in there that nobody actually notices, and that the information that comes from that gives you what you need. So it's really going to be more of a case of how do we modify what we do to give us enough information to do something, rather than can we develop a new technique. It's probably going to be the next level up of the system design. But it's a fundamental problem called persistent excitation, and there won't be any algorithm that can do a lot better than that. You do need that information content to be able to do something.
If we have a last question, okay, then I'd like to invite the audience to thank Daniel again for that great talk.
Thanks very much.